It's an honor to be here today. About 2 years ago, I was also at the Driving Steel event organized by Tata Steel, and happy to pick up where we left the last time and show you what we're doing, where we're heading, and what kind of material challenges we're dealing with, and how those can also improve what we're promising with Hyperloop. So happy to take you through our story. The first part of the presentation will be mostly about what a Hyperloop is, what kind of world we envision we can realize with it, both on a sort of inspirational part, as well as just more into the content, like what can we really achieve with this. And the second part will be more about the material challenges that we're dealing with. So I think let's get started. First of all, I would like to welcome all of you to the world of Hyperloop, which is, in our vision, a world where in 2050 you can travel over an entire continent by Hyperloop as if it is one sustainable metropolis, right? An entire continent can be actually one city, and at the same time that the supply chains on an entire continent are also connected within several hours, which allows basically an entire continent to be a single market, same day delivery on an entire continent, and really change the way in which we now deal with logistics. So this is our vision. But what is actually the challenges that we're dealing with to get here? Well, first of all, if we look at transportation right now, the demand for passenger and freight transportation is forecasted to grow by about 2.5 times towards 2050. And these are the most recent numbers, even taking into account everything since the COVID situation. And in order to accommodate this growth, it is estimated by a subgroup of the G20 that about 96 trillion euros need to be invested into infrastructure worldwide. So that's really an unfathomable large number. But the key here is that we invested into future-proof transportation. And what we've already seen now is that the current modalities are already responsible for about 30% of all greenhouse gas emissions, which means that if we keep investing into the current modalities, we will not be able to accommodate this growth of 2.5 times. We simply will not be able to do so. So key here is that we invest into future-proof transportation. With the Hyperloop, we see really that we have a puzzle piece for this puzzle to really make a big difference in being able to accommodate this growth sustainably. So the Hyperloop is faster, greener, better, and smarter than the current modalities that we have in hand. I will now go a little bit more into each of these different points. So the first point is the Hyperloop being fast. First, very quickly, what is the Hyperloop? What I actually am talking about? It was originally proposed by Elon Musk in 2013. The story goes that he was sitting in his car in traffic between Los Angeles and San Francisco, thinking, shouldn't there be a better way to do this? And then realizing that we're investing tens of billions of euros into a high-speed rail connection there. But surely there must be better ways, actually more competitive ways to actually deal with these issues. So it was proposed by Elon Musk and sort of brought open to the market. The basis of it is that it's vehicles traveling through a low-pressure tube, which means that you have very little air resistance and therefore almost no energy usage while you're traveling, allowing you to go to very high speeds, aircraft speeds, with only a fraction of the energy usage. Now, in the original concept, there was a different type of suspension than is now commonly used for Hyperloop, but he invited innovators to really develop it and pick it up. And right now, the consensus is really that Hyperloop vehicles are suspended and propelled magnetically, which has the additional benefit that you don't have the air friction, but you also don't have any friction with the rail. So this means that you have very little drag due to friction as well. And since there's no touching of the tracks, there's also very little wear and tear, and therefore very little maintenance. So this gives completely different requirements on the infrastructure. But this is really the basis of a Hyperloop. Now, why is it faster, greener, better, and smarter? Let's go into the faster part first. And let's just take, for an example, two cities about 500 kilometers apart from each other and compare how you would travel between these two cities with a Hyperloop and with an airplane. So off both of the systems go. The nice thing about the Hyperloop is that it goes directly from city center to city center, and that you travel with about 700 kilometers per hour on average, allowing you to reach your destination in about 34 minutes. And that was about the time that you had spent on your airport actually waiting to go to your airplane, taxiing to taking off. And the moment that your flight has taken off with the airplane, the Hyperloop has already gone back and forth and is going back towards its destination for a third time. Airplane is slowly descending now, landing, and as the airplane is taxiing towards the airport, Hyperloop is already back on its fifth trip. And at the same time as you've taken one trip with an airplane, Hyperloop has gone back and forth about 5 times. So this is really the difference between Hyperloop. It's not just, approximately the speed of an airplane, but because you don't have all the other stuff around it as well, such as taxiing, such as all the time on the airport, it's about 5 times faster in total. It's also much greener. If we take the same distance and we look at the amount of CO2 emissions per 100 million passengers traveling on this distance, for a Hyperloop, if we can manage to have this system powered fully by renewables, this would be 0 tons because it's completely electric right from the get-go. If we would take the current generation mix for energy into account, it would be about 1.2 million tons. But compare this to about 7.7 million tons of aviation right now, showing you the huge difference in energy consumption between the two systems as well. Of course, there's not just the energy mix for the emissions, right? There's also the emissions for the construction, which is really a material topic. And I'll go into that a little bit at the end of the presentation as well. So this is about 5 times to infinitely times if we manage to do this powered completely by renewables. It's also better on lots of other aspects that you might not think about right from the start. It eliminates external factors because the tube protects from the environment, no wind, rain, no snow, no leaves on the track, and because it's automated, it's completely void of human error. Because it's completely automated, the arrival times are also predicted to approximately 1 second. So this is completely different from the delays that we're used to for aerial and aviation. If you compare the land take of a Hyperloop versus the land take of, for example, a road, these two things have the same amount of capacity. They can transport the same amount of people per hour per direction. But a Hyperloop only takes about 2 meters of land per linear meter, while a car road takes about 50 meters of land. So when you're thinking about a Hyperloop polluting the landscape, think about what highways are actually taking into account, right? So this is a huge benefit that we have with a Hyperloop. We can integrate this alongside existing infrastructure, existing highway, existing railway very efficiently, and therefore minimizing the actual intrusion into the landscape, which is one of the major bottlenecks of implementing high-speed rail right now. And finally, it's also much smarter. So let me give you an example of why Hyperloop is so much smarter, and this is because we can really tap into network effects. So this is how it looks like. It's very much like a highway where you can have vehicles merging out and into the system at any moment in time. This is what a magnetic levitation switch traditionally looks like the one that has been built in China. As you can see, to be able to make a switch, the entire track, tens of meters of concrete has to be bent. You can understand what it implies to be able to do something like this. Now compare this to our switch, where nothing in the track is moving. It's only the vehicle selecting which track to follow and simply pulling itself towards that track, making a switch without any moving components. So rather than a track that is stuck sort of in between, blocking all transport, destroying network capacity, and forcing deceleration while switching, we enable high network capacity and allow high-speed switching and lane switch. And let me now just show you what kind of transformative benefits you can have by doing something like this. Let's take, for example, a connection between Netherlands and Germany. There's really three key areas here. You've got the Randstad, which is about 8.3 million people. You've got the Rhine-Ruhr area, which is about 10.7 million people. And you've got Berlin, which is a metropolitan area of about 6 million people. Now, with one Hyperloop network, you can do all of these things. One, within the Randstad, you can go from any origin to any destination within about 10 minutes, turning this entire agglomeration really into one city. You can do the same in Rhine-Ruhr, where you can go from any city within Rhine-Ruhr to any other city within about 10 minutes. But instead of these being two separate systems, you can connect all of this with the same line and travel within any city from any origin to any destination within this entire corridor within about 1 hour. So what we're talking about here is 25 million people connected within 1 hour, which is the same scale as a city like Shanghai, where it actually takes a longer time to go from one part of Shanghai to the other side of Shanghai than it takes to travel within this entire network. So this is really the true transformative benefit that you can have from Hyperloop. It allows you to alleviate the housing issues in these very big metropolitan areas by basically spreading it over all the other areas on the network as well. You don't have to build warehouses along every city anymore, because you can just build one hyper hub that will allow you to basically replace 10 local hubs while still allowing same-day delivery across the entire continent. You can free up capacity at these air hubs. Heathrow needs to build a third runway, which costs about 20 billion euros, which buys you about 600 kilometers of Hyperloop. And once you've built 600 kilometers of Hyperloop, you don't even need to expand Heathrow anymore. And this is the same, for example, in Amsterdam Airport, and same along all these other EU hubs. And you can really get into the heart of the cities, which is really not that easy with other modalities. And in the cities, you can integrate directly with bus systems, train systems, with walking and cycling modalities, completely changing the entire transport steps. Now, in order to be able to do this, we need to have a standard, right? Because such a network can only have its effect once you can go from any place to any other place, right? So you need to be able to have one standard from the start, and therefore we have initiated the setup of the European Hyperloop standards, and this is already up and running now. Right now, all the Hyperloop companies are working together within this group to make sure that we achieve single interoperable standards. So this is really going to be the basis also for the global standards, portable worldwide. So what are the steps are being taken to realize this Hyperloop? Well, I told you already about the first Hyperloop concept by Elon Musk back in 2013. Then he launched a competition where he asked people from around the globe to build the first Hyperloop pod to test it in his test track there. We won that competition and then launched Hard Hyperloop, from which I'm talking right now. And one of the first steps we did was build a test facility in Delft. And I would also like to show you a little bit of what we've been doing here, because Tata Steel was also one of the major contributors to this facility. So I would like to just show you a little video also of how that went. Yeah, that works.
So in the test facility we have in Delft, we are testing every component that Hyperloop needs to operate. We do that at full scale. And the latest we've come up with is the Hyperloop switch. So based on our hybrid magnetic levitation and propulsion, we can actually create connections to tubes that are a bit like a highway, in which vehicles go on, they join the main line, and then they can go off at any point. This is the beginning of the European Hyperloop network that stretches more than 10,000 kilometers across national borders.
Into this test facility, we have built the three core systems of the Hyperloop, namely the levitation, which is the component that allows the vehicle to lift off of the ground, creating zero friction with the track and remain at a stable distance from it. In addition to that, the vehicle is now able to propel back and forth, which is what we call the propulsion.
So once the vehicle is moving, we use lateral tracks to actually keep it in place. And when we need the vehicle to go from one track to the other, we pull them towards one track. This way we can decide where do we want the vehicle to go. All of these components were tested in our facility at Delft, in which we have a near vacuum environment. Everything is controlled, and we test everything simulating real vehicle weight and size.
What is great about the realization of this facility, that it's not just the work of a single startup, but it's really an ecosystem that has been working together on this. So all of the different subsystems that are being tested in this facility are already co-developed and supplied by partners right now.
Steel is a vital component of sustainable future mobility. Drawing on Tata Steel's high-tech innovation skills and materials expertise, we support the development of Hyperloop.
2 years ago, we started our relationship with Hart. And in the meantime, we have created a working system.
Especially during the whole process of getting this Hyperloop test facility finalized project, there will continuously more and more partners adding to help and to make it a reality. I feel extremely grateful about that. Especially the team has done such a tremendous effort to get it finished on time and make everything work. So it's really amazing.
That's successful. Nice. Thank you.
The next step after this, after having built this facility, was to set up a broad Hyperloop development program, in which we have all these partners working together, supported by the Dutch government for economics and infrastructure, to develop and test Hyperloop together with public and private partners in the European Hyperloop Center. So this is the next facility that we're now developing. It's a test track of about 2.6 kilometers distance, which will allow us to test at very high speeds, up to 700 kilometers per hour, and crucially show that you can also switch by merging out and into a tube. So that's a very important part of what we're now testing, and we're already building the first infrastructure and magnet prototypes to be able to test in this facility. The next parts are really that we're looking for a commercial cargo route to to build a first route, because we believe we can get to market faster by doing something for cargo first. There's a very interesting route we found in the Netherlands, in which we can basically reduce the travel time of about 3 hours to 30 minutes between the major auction houses here for flowers. And this is already 64 million euros of financial and equivalent socioeconomic benefits for just a project size of 800 million. So this is really a very interesting first potential route, and there's about 30 stakeholders who support this. And all of this should in the end work out to building a network across the globe, where, for example, a European network like this would already net about 20 to 40 billion euros of annual revenue. But now let's get a little bit more to what the materials challenge is as well, because this is, of course, also the main subject of why people are coming together today. Actually, this image here is actually one that our counterpart at Tata Steel shared with us quite a while ago, which is that 1% of this system is actually a vehicle going through it, but 99% of the time you just have the tube and the tracks, right? So if you really look at where are most of the costs of a Hyperloop, it is basically the infrastructure. And where we see most of we see a lot of potential in having a steel tube, and we need to have steel tracks in order to be able to levitate inside this tube. So steel is like what Tata Steel just said in the video. It's a vital, crucial component for the future of mobility. I wanted to get a little bit more into what Tata Steel, for example, has already been doing on how to basically see how we can reduce the cost of the entire system by being innovative with materials, right? So on the one hand, you've got all these different types of tube methodology you can use. A tube in a tube, where you give it extra stiffness by increasing the distance between the outer and the inner layer. Folded tubes, which give extra ribs to also make the tube much stiffer against this pressure load case. Or maybe even segmented tubes, so that you can transport the tube in pieces, because you can imagine if you want to build a Hyperloop and you have to transport tube sections of 3.5 meters all over the place, that's also going to be quite a big challenge, right? So if you can build this more modular, that is also a very, very interesting thing to look at for Hyperloop. I see an interesting question in the chat that I can immediately comment on. If there's any known materials that can withstand the depressurization which had happened in Hyperloop in case of an accident. So on the one hand, you see here these structures. These are really meant to deal with the pressure load case of air pushing on the outside of the tube and ensuring that the tube stays stiff. At the same time that the tube can take a nice long span between columns, so you don't need to put as many columns in there. But of course, there are situations where you have a depressurization, for example, because there's a leak somewhere. It's interesting to note that even if you make a leak that is, sort of at the size of a big football, the air leaking into the tube is limited by sort of an effect at the edge, which means that it can only go in at the speed of sound at that little thing. If you compare that to how fast the air goes into the tube, that is actually very limited. So the load case of air rushing into the tube is actually quite insignificant compared to the load case of the pressure on the outside of the tube. So it's a good question, but it appears that the dynamic load case of that one is not as significant as just trying to maximize the resistance against the external pressure. And here's a nice image of interns also working at Tata already realizing some of these concepts for different tube types. And this is, for example, how actually the Hyperloop could look then with one of these innovative systems. Another interesting part also on steel here is that the tracks are actually one of the most difficult parts because typically there's not many applications where you need a track that is laminated. So the track of a Hyperloop is laminated because once you pull a magnet across the track, you generate little currents in the track, and that is akin to actually losing energy. So if you make little laminated pieces in the track, that means that you cannot have these currents and therefore have a much more efficient system. But traditionally, there are not really a lot of applications where you need to have very long laminated pieces. So one of the major costs that we have right now is actually the machinery able to laminate very high volumes of very long tracks, because that is the most efficient way to build this, right? Not having very lots of short pieces of track, but very long ones. So that's also a very interesting material challenge that we're dealing with. To give you a little bit of a comparison of how much steel is needed for this, the entire European network of 10,000 kilometers needs about 1,500 kilotons of track. And the current EU market is about 1,000 kilotons, right? So this is quite a substantial fraction of the market. Of course, you don't build it in 1 year, but even split over a few years, this is quite a big fraction of the market. Then I will finalize this slide before going into the last, before going into the question. I said earlier that a Hyperloop, if powered by renewables, could have zero emissions, right? But of course, we also need to take into account the emissions of building the Hyperloop in the first place. And a large fraction of the construction is the steel and the concrete needed to build the Hyperloop. Now, if you compare Hyperloop to the other modalities and how much energy they use, you can see here are the fuel-based systems. These are the ones that are already powered by electricity. And we're now assuming what would aviation here also powered by electricity. You see that Hyperloop is actually by far the lowest energy consumption from all the other modalities. But very interestingly here, you see that we have two scenarios for Hyperloop. Either it's low occupation, and with low occupation, we simply mean that we only replace air, right? You build out a European network and you only replace the aviation on the continent. But as I showed you, you have all these network effects. You can go much further and you can have much more occupancy, have many more people use it. This is the difference here. If we only replace air, then you see that the construction of the infrastructure is quite a large component of the entire energy usage. But if you have many more people using it, it becomes almost negligible. Then it's just the energy usage of the operations. But when we're building up the network, of course, we're not using very high occupancy yet, right? That's building up as the network grows. So especially in the very early stages of a Hyperloop, the emissions for construction are especially important. So this is actually one of the challenges I also like to put out, is how can we build hundreds of kilometers of steel tubes, basically, with as little CO2 emissions as possible? Because especially in the early stages, the CO2 emissions of the construction of the tubes is actually going to be the biggest contributor to the emissions. So this is a nice challenge to think about. Already read in the news some time ago that the ambitions to reduce emissions of the production of steel by about 80% by using hydrogen instead of just coal. So that's those are very interesting, and those would really make a huge impact on the emissions of Hyperloop. So that's what I really wanted to share on the material aspects. So thank you for joining on my presentation. I see already that there's lots of nice questions in the chat, and I think there's still sufficient time left to go into those.
Thank you, Mars. Great presentation. Once again, thank you very much for that. Not only a lucid presentation, but also thought-provoking. And I suppose my colleagues who have joined, particularly from the steel fraternity, would really like to take up on your challenge of CO2 on tubes. And at the same time, I'm sure they're also happy to note that steel will continue to be a big player. As you said, 99% of the construction is steel. Okay, and I hope we will make sure that it is the material of choice, not just because it is steel, but hopefully it will become the material of choice. So one other thing I want to just place before we get into the questions is, it's not only through your presentation have we been able to really imagine how revolutionary the entire idea is from the point of view of making transportation sustainable, from the fundamental ideas. But I think what I particularly take out and take away from the presentation, and I'm sure most of my colleagues who have joined in, all the participants, is the transformative effects it has on society at large, whether it is economic or whether it is environmental or whether it is with respect to quality of life, etc., etc. I think the transformative effects of what you just showed with connecting 3 high-density parts of the European continent itself is quite mind-boggling. And I think that's where probably what it will, or that is what will probably drive Hyperloop to become a possible option for the future. So thank you very much for taking the time out and giving us a presentation. Let's now get into the questions. Firstly, I think the audience also echoes the same sentiment as I did, Mars. So thank you for this. You already answered one question on energy, sorry, not on energy, but you spoke about depressurization, and you kind of answered that and the principles why it is not, or the scientific principle why it is not really a big issue at the moment. The next question, as it comes up here, is there's a question on the energy conversion. And it says that whatever energy you supply to the inside vehicle to move it will eventually get converted to heat.
Yeah.
And how are you planning to dissipate it? That's a good question, actually.
This is absolutely one of the biggest challenges of Hyperloop. It's also one of the first things that we thought, ooh, this is difficult, because usually, you put some kind of a radiator or something. But since we are now in a low pressure tube, there's not really any way to get your heat dissipated anywhere. So there's a few things that we have come up with to deal with this. First of all, what we're really trying to do is minimize the amount of heat that's actually generated inside the vehicle, right? So therefore, we put all the motor systems so outside of the vehicle for the to make sure that those inefficiencies end up in the track where it's more easily dissipated to the outside environment. the way that the magnet works is also that almost all of the power comes from actually a permanent magnet. So not really power, but most of the force comes from the permanent magnets, and that we only stabilize around at equilibrium. So that only takes about, I think, 300 watts of energy per ton. So that's not a lot of energy that we use for that. And the rest of the energy is simply for the life support systems. So we just really use a very low amount of energy. So that's actually the first way to deal with this, try to dissipate as little energy in the vehicle as possible. The ways in which we are dealing with this, I can't say too much about it, but we're looking at mostly techniques that use evaporation within sort of confined environments within the vehicle. So that's the most thing I can say about that.
Yeah, right. Thanks, Mark. Like evaporative cooling, etc. Okay. The next question, I think you have kind of through your video and others kind of, indicated, but still there's a question, and you might want to enlighten the audience, is how mature is the technology right now? So maybe you could give some points for people to appreciate what it is, where it is now.
Yeah. So the first passengers have already traveled with the Hyperloop, right? That's in the test track in Nevada of Virgin. People have already been in the Hyperloop in a low pressure environment. They didn't go up to 1,000 kilometers per hour, but all of this is in a stage approach, right? Because we need more length to be able to actually test at that speed. But so we can. The only way to do that is that you actually have solutions for all of these different safety systems, right? The thing is that it hasn't been completely certified yet for commercial use. So this is also what the goals is of these new test facilities. It's not just a test, but it's also a long-term certification facilities where we can do multiple year projects to actually get this thing certified. Basically, all the components that are used have been tested as subsystems in separate environments, and we'll be using the next years up to about 2025 to really test everything, have it built, come 1 and 2 years, have it tested, so we can start building the first route somewhere around that time as well, 24, 25. And that actually is one of the other questions already. Can Hyperloop be used for cargo? Just because I'm already saying this now, can also answer that one. We really believe that a first route would be very beneficial if it would be used for cargo. And it is very nice that we actually have found a route that is on itself is actually profitable with cargo. And on the other hand, if you look at what you can do with cargo by basically having one hub that transports goods towards cities and not having to duplicate warehousing, stock, and processes near every city, I think it's going to be very big cargo for the Hyperloop. Yeah, absolutely.
That's right. That's right. So there are a couple of questions, I think, which you kind of answered. It's about speeds and things like that. So you kind of indicated what's the kind of speeds you're looking at. You also said what are the test speeds that we have achieved. So let's just get on to the other question, which is how do you compare Hyperloop developments between Europe and the United States? I guess Europe is far ahead of the rest of the world.
No, I think the first thing that should be said is that we work together quite closely. We have meetings every few months organized by the European Commission, in which the Hyperloops from the Hyperloop companies from the United States also join, and where there's also conversations between European Commission and the FRA, the Federal Rail Authority of the US. So they are working together. The US is also now preparing for a certification facility. The nice thing is we are coordinating these efforts also by the standards, right? So we're already discussing on the making sure that we go towards one system. In the end, I think it's going to be really like a space race. I really like that analogy, right? We are both, everybody's seeing what this can be, and we're all working hard to get there as fast as possible. I like this kind of competition while still working together to make sure that we arrive at a single standard. Yeah.
Right. Thanks, Mark. Yes, I think that's what will probably drive the developments and commercialize and make the commercialization faster. Yeah, on the next question on steel, you have already answered about so many tons required and stuff like that, including the electrical steels that you would need for building the tracks and the levitating systems. There was this one other question, which is on if these hyperloops were to be built underground, would they be more efficient and easier for infrastructure? Are there thoughts around it?
Excellent question. So we deliberately always say Hyperloop can be built both above ground and underground because it really depends on the situation. If it's an environment where you have reasonably high amount of space, right, where you can just implement it, for example, along an existing highway or railway, then it's easier to just put it on columns, have it above the ground. However, there's lots of places where that's very difficult and where you have to build a tunnel, right? Tunnels are always, if you have to, then you just have to build a tunnel. The big difference is that one Hyperloop tunnel per tube is about 3 meters, 3.5 meters in diameter. If you look at a tube, for example, even for a metro, that's already 6.8 meters in diameter. And so it's about twice the size in diameter, but that means it's 4 times the size in area. So we do really believe that a Hyperloop, because it's so much closer around your vehicle, that we can build much lower cost tunnels. And so when you need to, we can probably do that for lower cost than other modalities.
All right. Yeah. Thanks. Thanks, Mars. There's another question on safety aspects when you're moving at such high speeds. Anything you might want to add further on the safety aspects to make sure that things don't go wrong?
Yeah.
Or if they go wrong, how would you take care of it?
And so the by far number one safety crucial component for passengers is the door, right? Because it's a component that opens very often, right? It's a dynamic component, but if it accidentally opens while you're in the tube, that's of course a very big hazard, right? So we need to be able to ensure that the door can never open, right? But it could also be that there is some kind of a leak inside the vehicle, and that means that you need to be able to at any point, if you need to be able to evacuate, to be able to slow down the vehicles, repressurize a part of the tube, and then have it very similar to any type of tunnel evacuation. So that's exactly what we're doing, and that's also what we will be testing at the European Hyperloop Center, is this repressurization mechanism. And all these vehicles in the tube are basically also virtually coupled to each other. So if one vehicle is moving forward and there's a calamity further ahead, all the vehicles behind it will slow down together in sort of a virtual train. So that's the way in which we ensure that you can also have that you can slow them down together.
Yeah, thanks. I think we have kind of come to the end of the time that we have. Just one question, if you can. This is talking about, and just to clarify, the question has come in saying that only one vehicle can move inside a single Hyperloop tube, and how can you increase or accommodate higher occupancy is the question. You might want to clarify.
So it's much more like a highway where you have many vehicles behind each other and then merging out and in, rather than a single vehicle. Yeah.
Right. Thanks. So I think that's it. We are past 4 o'clock India time. Mars, once again, thank you very much for that brilliant presentation. It gives us a lot of hope in terms of where Hyperloop today is and how it's progressing into the future. And I think the way you have articulated the benefits, I'm sure a lot of governments, policymakers, and industry, academia, all of them would be looking at making it a success. So once again, thank you very much for taking the time out and being at the conference. Really appreciate your efforts and wishing you all the best. Stay safe and stay healthy.
Yeah.
Thank you.